In this video, we are going to solve the differential equation y prime equal y over x in 7 different ways. The methods include the separable method, integrating factor method, homogeneous equation method, quotient rule, and an ad hoc method, and the series solution method and an Anzast method. So let's look at one by one. So let's start with the most common one for a problem like that. So we have a problem y prime equal y over x, and you can see that this is a separable differential equation. So so we have y prime equal y over x. So first note that y equals 0 is a solution. Is a solution. If you plug in y equals 0, you can see that it satisfies both equations. So suppose to find the other solutions, suppose y not equal to 0, and what we can do, we can divide by y both sides, and dividing by y, we can write this one as dy over y equal dx over x. Now what we can do, we can integrate both sides. So integrating we have on this side ln absolute value y equal, on the other side also ln absolute value x plus c. Now what we can do, we can write this one in the exponential form. So when you write this in the exponential form, you get y equal e to the ln x plus c, and then you can write this one as e to the ln x times e to the c, and e to the c is just a constant. And then also removing the absolute value, we can write this one as y equal plus or minus. The plus or minus comes because we remove the absolute sign, and then e to the c, and we have eln get cancelled, so you can write this one as absolute value of x. Now when we have the absolute value x, you can see that that is giving a non-differentiable function, so we remove the absolute sign to get a differentiable function. That means it's going to carry a plus or minus sign that we're going to incorporate with the plus or minus before that. That means we can write this one as finally plus or minus e another c. The c's are different x. Now what we're going to do, we're going to consider this plus or minus e to the c as one constant, so you can call that is a, so that means you're going to get ax. Now you can see that, so a is any constant. A can be 0. When a equals 0, you get the y equals 0 solution. So a is a constant. A is a constant. We normally call the arbitrary constant. So that is a solution using the separable method. So let's look at the next solution, which we can use the integrating factor method. And you can see that why we can use integrating factor methods. So let's look at the problem. So you have y prime equal y over x, and then you can, if you bring all the terms to one side, we have y prime equal y over x equals 0, and you can see that this is the first order linear differential equation. And in this problem, you can see px is equal to negative 1 over x. So we can find the integrating factor. Because this is linear first order, so I'm going to write this one. This is a linear first order. Linear first order. So normally to solve linear first order, we use the integrating factor method. So integrating factor, we normally write I, which is e to the integral of px dx. So which is e to the integral of negative 1 over x dx. And pulling the negative sign out, we can write this one as e to the negative ln x. We don't write the absolute sign here for ln because we are looking for only one solution. So we can write this one as e to the ln 1 over x. Now what happened again as before, eln get cancelled, so you get 1 over x. So 1 over x is the integrating factor. And from the theory, we know that after that what will happen, your equation is simply, due to the product rule, this simply becomes the derivative of You can write this one as a derivative of uh, integrating factor times y. So that's the theory part. Because you can see that if you use the product rule, that's exactly what you're going to get. So this says that the derivative is a constant. That means y over x is a derivative is a zero, so y over x is a constant. So this says that y equal c times x. C is a constant. C is a constant. Okay, that's how you get the solution using the integrating factor method. So let's look at the homogeneous solution method. Homogeneous solution. And why this is a homogeneous solution? You can see that this equation is in homogeneous form because y prime can be written as a function of y over x. So it is already y over x. So these are what we call homogeneous equations. That function can be written as y over x. So for problem like that, what we normally do, we use the substitution. So we're going to use the substitution. This is standard theory. Y equal vx. So that's the standard substitution for this kind of problems. And then what we do after that, we take the derivative. So when taking the derivative, you can write y prime equal v prime x using the product rule, and then v x prime, which is 1. So that means so this is simply v prime x plus v. Now we can substitute that into the differential equation, and y of x you can substitute as v. So you can see because of this one, v equal y of x. So wherever we see y of x, we can plug in v. So that means using those two, we can write for the derivative part simply becomes v prime x plus v. Y of x become v, and then you can see that these two get cancelled. So what this says, v prime x equals 0 divided by x, because this is independent variables, you can divide by that. So the v assuming not equal to 0, v prime equal 0 assuming x not equal to 0. So this says that with the derivative of v is 0, this is that v has to be a constant. Now since v equal y over x, so it says that y over x is a constant, and then multiplying by x, y equals cx as before, where c is a constant. So that's how we use the homogeneous solution method. So let's look at the next one, which is the quotient rule. So let's see how we can use the quotient rule here. So we can start with the equation y prime equal y over x. Now we can make an observation. So and then we can rewrite this one as x y prime minus y equals 0. And then what we're going to do, you can see that we can divide this equation by x squared assuming x not equal to 0. So x y prime minus y times 1 divided by x squared. We assume that x not equal to 0. So then what happened? You can see that this is just the quotient rule applied to d over dx, the quotient of y over x. Because if you apply the quotient rule, that's exactly what we get. So you can read it like that. And this says that the derivative is 0. That means the y of x has to be a constant, which is c, and then y equal c times x as before. So that's how we use the quotient rule. So this is the quotient rule. Good. So let's look at the next method. The method number. Next we discuss a ad hoc method. I found this method from one of the videos of CyberMath. So how we do it? So we're going to start with y prime equal y over x, and then we can rewrite this equation as y equal y prime x by multiplying. Now what we can do, we can take a derivative. So taking a derivative with respect to the independent variable. On the left side, you're going to get y prime. On the other side, by the product rule, you're going to get y double prime times x plus y prime times 1. and you can see that these two get cancelled. So you're gonna get y double prime x equals 0. In other words, y double prime equals 0, assuming x not equal to 0. So this says that y prime, because the double prime is the derivative, y prime has to be a constant. Now, if you integrate one more time, you're going to get that y equals cx plus d. Now the problem is we have this extra d, and then what happened? This is the reason, because when you take a derivative, this is like squaring an equation. It's going to introduce more. So in this case, what happened, when you take the derivative, all the constant term get cancelled. So that means you have to check whether this solution is a solution of the original equation. So that's something you have to remember. So that means if you plug in this in the equation, so you can see we're going to plug in that in this version. This will be much easier. So if you plug in that to the both sides, so what happened, you can see on the left side you have cx plus d. On the other side, y prime equals c, so this cx, and you can see that cx get cancelled. So this says that d equals 0. So since d equals 0, you finally get the solution. So y equal cx. So you have to be careful with when you take a derivative. You always have to check whether the solution is the solution you obtain is the actual solution of the original equation. So that's something you have to remember. Okay, so next we can talk about the series solution method. This is one of the very important technique, because sometimes this is the last resort for most of the some of the problems that you can solve using any of those methods that we discuss. So let's talk about that. In the series solution method, what we're gonna do, we're gonna assume the solution is a series. So we assume y, the solution is in the series form. So n going from 0 to infinity, a n x n is a solution. So we assume this is a solution. Is a solution of the equation which we can write as y prime equal yx, but you can look at the other version. So now what we can do, we can take the derivative. Okay, so take the derivative. Once you take the derivative, y prime equal, what happened, you can see that n equals c, when you plug 0, this is a constant. The constant term goes away, and then you have only the rest of the term. That means n can start at n equal 1. So, and then once you take the derivative, it is a n times x n minus 1. That's what happened. So you lose the first term and you take the derivative. So that is the y prime. Now what we can do, we can substitute this in the equation, but we can write the equation as x y prime minus y equals 0. So we're gonna substitute in this form. And then so we can see, so we have, again I'm going to write that part. So y prime equal y of x. So we can write this one like x y prime minus y equals 0. Now what we're going to be substitute. So by substituting, so if you substitute, you're going to get x y prime that we found, which is n going from 1 to infinity, a n times a n n times x n minus 1, and then minus y, which is the original one, n going from 0 to infinity, a n x n equals 0. So then we can bring this x inside. So that means you can write this one as n going from 1 to infinity, a n, this become x to the n again, minus n going from 0 to infinity, a n x n. Now what we're going to do, we're going to write the uncommon first and the common terms separately. So because for example, when you plug in n equals 0, you get a term which is not common to both sides, because we try to get the same index for x. That's the goal. So so let's plug in a 0 for the second one, and then leave the other common terms. So let's do that. So that means we can write this one as n going from 1 to infinity, a n n x n from the first one. From the second one, I'm going to write plug in n equals 0. That means you get a naught, and then the rest I'm going to write as n going from 1 to infinity, a n x. That's the rest of the term. That's what we always do. Now we can combine these two terms, because you can see that they have the exact same power. So you're going to combine them. So if you combine them, you can write this one as sigma n going from 1 to infinity. And you can see this is going to be, there's a subtraction. So that means you can write this one as n minus 1 a n x n, and then we have minus a naught term. And you can see that the two sides has to be the same. So that means one side has a 0, the other side has to be 0. So this implies that a naught has to be 0, and the coefficients, all the coefficients also has to be 0 because the other side is a 0, and all the coefficients, that means n minus 1 a n has to be 0 for all the other index. I mean n going from 1 2 3 like that. So this is very interesting. So this says that a naught equals 0, and also, and you can see that this term is 0 if n equal 1. So that is the only time that this can be non-zero. For all the other n values, you can see that since we have this term which is not equal to 0, a n has to be 0. So this says that, so this is very interesting, this says that, so this implies that a naught and a2 up to everything, all the other terms are 0. So this says that only a1 can be non-zero. So only non-zero term, only non-zero term is a1. So that means the solution is y equal a1x or cx. So that is how you use the series solution method for a problem like that. It's very simple and interesting argument. So let's look at the final version. So the next one is the Anzast method. So we first make observation. We have y prime equal y over x. So this is that x y prime equal y. So what's going on here is, you can see that once you take the derivative and then multiply by x, you get the function y back. So that means this suggests that y can be a polynomial. So that's like a good observation. So we're gonna guess, so that's the answer. We're gonna guess y equal a n x n a n minus 1 x n minus 1 like that. So so we have a1x a naught. What we can do, we can take the derivative. Once you take the derivative, you're going to get y prime equal a n n x n minus 1, and then here you have a n minus 1 n minus 1 x n minus 2 like that, and then we have 2x plus a1 a naught term get cancelled. Now what we're going to substitute. So we're going to substitute. So we have x y prime. So that means if you multiply by x, the y prime terms, you're going to get a n n x n back, and then this is going to be a n minus 1 n minus 1 x n minus 1 like that, and then we have 2 a2 x squared a1x. This has to be equals to the y term, so that means it's be a n x n plus a n minus 1 x n minus 1 like that, a2 x squared plus a 1x plus a naught. So what we can do, those two are the same thing. So that means all the coefficients has to be the same. So this suggests that a naught has to be 0. So this one has to be 0. And then we also notice that we have the a1x term on both sides. So that means a1 can be anything. But all the other terms, you can see that they have different coefficients. Since they have different coefficients, the coefficient has to be 0. So that means this suggests that a n minus 1 all the way to a2 and 0 are 0. So only thing that can be non-zero is a1. So this suggests that y equal a1x is the only option, or otherwise we can write this one as y equals cx. So that's how you can solve the problem in the Anzast method.